environment without extending our reach further into space. The formation of the solar system likely began within a disk of plasma spun off from a rapidly rotating young sun. Within this superheated plasma, intense electromagnetic radiation created unique conditions for a phenomenon called polarized fusion, in which the magnetic orientation of atomic nuclei allow for the creation of a rich spectrum of chemical elements, including those heavier than iron, without the violent forces of a supernova usually used to explain their formation. These materials were then distributed according to the harmonic ratios discovered by Johannes Kepler, and condensed into the various planets, as well as the anomalous region in the dissonant interval between Mars and Jupiter that contains the asteroid belt. Meanwhile, anti-entropic evolution accelerated on the Earth. At first, primitive life relied on chemical energy sources within the immediate environment. As this process proceeded to exhaustion, life developed a crucial new technology for overcoming the finite resources of the terrestrial environment: photosynthesis. With the development of the chlorophyll molecule, life for the first time utilized an extraterrestrial energy source on a large scale, drawing energy directly from the sun. This too eventually led to a crisis, as the photosynthesizing organisms created a large and dangerous accumulation of free oxygen, a gas that was then toxic to all living things. Life surmounted this so-called oxygen catastrophe with the evolution of new organisms. With the movement of life from the oceans to the land, culminating in the development of the warm-blooded mammal, life again overcame existing limits to growth. We can trace the flow of such natural resources as iron to demonstrate the upward evolution of the three phase spaces of Vernadsky, from lithosphere to biosphere, and on to the cognitive domain of the noosphere, at no time reaching an entropic steady state of equilibrium. Roughly 2 billion years ago, the iron that had been created in the initial shedding of the young sun found itself homogeneously distributed, in soluble form, in our planet's seas and oceans. At that time, the newly emerging photosynthetic single-celled proterozoa began pumping oxygen into the waters and atmosphere. One effect of that biospheric upshift was the binding of the soluble iron with the oxygen to form a non-soluble compound which precipitated and concentrated into layers on the seabeds around the coasts of what were then continental masses. Those concentrated layers of iron ore became, in one particular area of the globe, the famous ore deposits of modern-day Minnesota and Wisconsin of the Great Lakes region of the United States, where they are mined still today. That same iron ore has subsequently been drawn into the noosphere, where it has been refined and further concentrated and formed into modern rail lines and urban infrastructure, increasing man's dominance on the planet, creating greater potential for human cognitive expansion. The next great barrier to overcome, leaving Earth's biosphere altogether, toward which all prior evolution has been directed, has been left to the willful activity of man. Along with the coming developments in nuclear fusion, we are in a position for the first time in human history to leave behind all the material constraints of the terrestrial environment. With the beginning of manned spaceflight nearly 50 years ago, and the first steps on the moon 40 years ago, the noosphere reached another phase in its evolution: the power to realize mankind's extraterrestrial imperative. We will begin this new phase of interplanetary economics with our nearest celestial neighbor, the Moon. The industrialization of the Moon is the proving ground for productive human operations in space, and will include the establishment of primary industries to build facilities on the Moon, and the export of a handful of precious commodities to Earth, such as the Earth-rare isotope helium-3. The Space Shuttle cargo bay could carry enough helium-3 to power the U.S. for an entire year, meaning that the crash development of the full spectrum of fusion technology to exploit this resource must accompany lunar industrialization. The lunar economy will develop in stages, beginning with nuclear fission-powered research, mining, and industrial facilities. Without a biosphere to concentrate certain minerals, the high energy densities of fission, followed soon after by fusion, will be indispensable in processing huge amounts of lunar material for the export of raw materials for further processing in orbital factories around the Moon or Earth, for the shipment of oxygen, foodstuffs, and other consumables to travelers on their way to Mars, or even more distant destinations, and for the supply of semi-finished goods to be finished in orbit for the spaceships and equipment to go to Mars, all supported by an integrated lunar infrastructure. With a flight time between Earth and the Moon of no more than several days with chemical rockets, and mere hours with fission propulsion, the entire region between the Earth and Moon will be heavily trafficked with freighters and personnel vehicles coming and going on a daily basis, utilizing a continually expanding orbital space infrastructure of communications relays, fuel depots, research stations, and production facilities. The sphere of human activity will thus extend from the entire lunar surface, through the region between the Earth and Moon, down to the entire terrestrial surface, including now inhospitable regions like the deserts, polar caps, and ocean floors that will be opened up by space technology. Once the lunar economy becomes self-sufficient, new cities, and with them new cultures, will emerge on the foundations of lunar industrialization, forming, in effect, Earth's seventh continent. The Moon will be the first extraterrestrial home of mankind.